before I started at MIT, stem cells were very well established. Mouse embryonic stem cells had been around for a while. Human embryonic stem cells were derived in 1998, but they hadn't yet been applied in these small-scale systems. And what we've been able to do over the last 10 years really is develop a set of tools and techniques, methods that allows you to use these cells in these micro systems and really bring together microsystems, microfluidics with stem cell biology. And so now people can ask their own questions of these cells. They want to study certain processes, and they can start to apply these technologies to those cells because we've laid the groundwork for this is how you do it. And in that process, we've shown that you can go all the way to actually answering important questions in stem cell biology using these technologies. And so that sort of points people in that direction of this is a fruitful area to go into. Stem cells are cells that have this interesting property that when they divide, they can either stay as a stem cell, so it's called self-renewal, or they can turn into something else. And what's so exciting about them is that if you can control those decisions, you could potentially cause that stem cell to turn into important tissues. So for instance, for regenerative medicine, or you could cause them to turn into tissues that would be important for testing drug toxicology. There's a number of uses for them. And the big challenge is, what is that recipe? So when you have a fertilized egg, you start with one cell and then that turns into you, and that's a lot of cells. And somehow nature has figured out this recipe to turn that one cell into all the cells in your body, and they have several hundred different roles depending on whether it's a heart cell or a muscle, so on and so forth. Okay? Well, if we could understand those recipes, we could turn stem cells into useful cells in your body. And that's been the major challenge in stem cell biology for the last 40, 30 years or so, okay, since the mouse embryonic stem cells were first isolated. So what's the recipe? And that recipe is controlled by interactions between the cells. So when the embryo is developing, the fate of the cells is controlled locally, meaning on the size ranges of hundreds of microns. And because we're able to manipulate things on those size ranges using microfluidics, we can start to do experiments that illuminate how those decisions are made and then potentially control those. So as an example, one of the things that we've been interested in studying is how the cells talk to each other in media, in liquid, that influences their decision making. And so they secrete molecules into the liquid, those molecules diffuse around, and then they interact with the cells around them. And that's been this essentially dark matter of signaling, meaning it's always there, everybody knows it's there, but since it's hard to study and hard to control, we just ignore it or try to work around it. Well, we developed these little microfluidic systems that allow you to control the environment around the cells very precisely so that you can turn that type of signals on and off. And you can study for the first time what happens if you remove all those signals. How are they important? How do they influence the fates, the decisions that the cells make? And of course, if you can understand and control those decisions better, you can better harness the cells for whatever the end application is. There's an increasing movement of taking some of these discoveries in stem cell biology and translating them to clinic or translating them to the pharmaceutical industry. And I think that we have a number of technologies that are relevant to that process, both because we can now set up systems that allow us to study decision making in these cells, which is important if you're trying to control them for either a therapy or you're trying to create a defined cell type that you want to have in a dish, as a disease in a dish. So I think as companies move into that area, that's something that we can contribute to. I think the other part of it, which is something that we haven't done in the context of stem cell biology, but we have a number of activities in terms of being able to monitor the state of the cells in sort of real time, which is important in bioprocessing. So if you're going to make a lot of these cells on an industrial scale, how do you know if the cells are good? You don't necessarily want to wait till the end of your process to know that they're good. So right now you might measure the pH in the solution, the cell counts, viability. But we have a number of other indicators that we've been developing, not necessarily for stem cells, but for other cells that give you insight into whether the cells are functioning like they were last week. And integrating those as companies set up bioprocesses, I think is a fruitful area.